Good morning, everybody. I am Vempati Srinivasulu, Assistant Professor of Chemistry, Nagarjuna Government Degree College, Nalgonda. In the previous lecture, we have started a new chapter, amines, cyanides, and isocyanides, part 1. Today, we continue same chapter, amines, part 2. In the previous class, what we have studied, a quick recap. In the first lesson, we have discussed what are amines, what is the classification of amines, how do we classify amines. Amines are the compounds, organic compounds containing NH2 as a functional group, or organic compounds derivatives of ammonia are called amines. These are two types: aliphatic amines and aromatic amines, depending upon the nitrogen link to nature of the carbon. And these amines are four types: primary amines, secondary amines, tertiary amines, and finally quaternary ammonium salts. Then we have discussed in detail for each and every type of primary amine with the different examples. Then we have discussed the preparation properties, preparation methods. We have 5 preparation methods in our syllabus. Out of 5, we have discussed 2 types of synthesis. Okay, one is ammonolysis of alkyl halide, and second one is reduction of amides. In this session, we are going to discuss remaining 3 preparation methods of amines. Those are Gabriel Thalamide synthesis, and second one is Hoffman bromamide synthesis, and third one is Smith's reaction. So let us take one by one. We'll discuss thoroughly. So first one, Gabriel Thalamide synthesis. So what is Gabriel Thalamide synthesis? So how it works, what is the mechanism, we will see. First, thalamide. What is thalamide? When it reacts with the NaOH, thalamide, when it reacts with the alkyl halide in presence of base like NaOH or KOH, and finally hydrolysis in presence of acid, it will give amines. These are the amines. So this is a thalamide. So one is base, alkyl halide, and water, aqueous acid. This is a Gabriel Thalamide synthesis. So in this method, we can, what are the different specific things about these synthesis. So with this method, we can prepare aliphatic amines only, the 2 primary amines. It is acid catalyzed hydrolysis of reaction. It is a acid catalyzed hydrolysis of amide. All in this reaction, alkyl halides are converting into amines, primary amines. We can't prepare secondary or tertiary amines with this method. We can prepare only primary amines. Okay, so what is thalamide? How can we prepare this thalamide? So thalamide is nothing but derivative of ammonia, derivative of phthalic acid. What is phthalic acid? Oh, this is phthalic acid. Benzene dicarboxylic acid. A benzene which has 2 carboxylic acid Generally we take in ortho position, that is phthalic acid. This phthalic acid, when it reacts with ammonia, first you take 2 moles of ammonia, it will give diamide of phthalic acid. This diamide of phthalic acid on rearrangement reaction, it will lose one ammonia molecule by giving one carboxyl ammonia molecule, it is giving phthalimide. This is a phthalimide. This is phthalimide. So this is a substrate we use for this specific synthesis. Okay. Then next slide. Okay. Then okay, you see, so this is a mechanism for phthalimide synthesis. So in first step, phthalimide is losing one proton to the base. You see, this is a base, this is OH minus. You take NaOH or KOH. When base reacts with this phthalic acid, that phthalimide, it loses one proton. This proton is lost. This side is lost as proton. Why? Because it is acidic in nature. The formed N minus ion is stabilized by resonance. So whenever a ion, maybe cation or anion formed as an intermediate, when it is stabilized, we can say that it is a stable intermediate. So this is a possible. So this is a acidic. This shows acidic nature. Phthalimide shows acidic nature. Okay. After losing proton, then it attacks on alkyl halide. This is alkyl halide. So in halide, X is a X minus, it goes as X minus, and at the same time this nucleophile attacks on alkyl group. So we can say this is an nucleophilic substitution reaction. So on nucleophilic substitution reaction, we'll get this type of N substituted or phthalimide. So alkyl substitute, R group is substituted on N in place of proton. So it is N alkyl substituted phthalimide. So this phthalimide on hydrolysis, what is happening here? This bond is breaking, this bond is also breaking. So amides on hydrolysis gives amines. We know that. So finally we are getting it is, this reaction is going on in presence of acid. That's why you'll get ammonium salt, halide salt of ammonium. At the same time, you get phthalic acid. Okay, this ammonium salt of primary amine on reaction with NaOH by losing one proton and X minus ion will get primary amine. This is, and you will get sodium halide and H2O. So this is the mechanism of this reaction. I repeat once again. You see, first this is a phthalimide. It loses one proton to the base, forming this minus 9 nucleophile minus ion, N minus ion of phthalimide. This acts as a strong nucleophile which substitutes a halide in alkyl halide. On nucleophilic substitution, we get this N-alkyl substituted phthalimide. This N-alkyl substituted phthalimide on acidic hydrolysis, it will give ammonium salt of primary amine and phthalic acid. Phthalic acid is regenerated. We can reuse this by adding ammonia, will get required phthalimide. On in NaOH reaction with the base, you'll get phthalic acid and primary amine. So this is the way we'll get primary amines in this Gabriel phthalimide synthesis. It's also known as Gabriel synthesis. Okay, this is a okay. Next, so in this method, using this method, we can prepare different types of amines by changing the alkyl group. Very simple. If you know the mechanism, if you know the general reaction, we can prepare whatever we require. So first of all, we take primary phthalimide, same NaKOH. Ethyl, you are taking ethyl bromide as an alkyl halide. In place of alkyl halide, you are taking ethyl bromide. What will get? Ethyl amine. Simple. So this ethyl bromide is changing into ethylamine. That's all. So this is an example for Gabriel synthesis to prepare ethylamine. So in the second example, we see this is a phthalimide. We are taking 2-iodopropane, is iodide, alkyl iodide. So this 2-iodopropane, we are getting, you see, what is this we are getting? You see, just wait, small disturbance here occurred due to net problem. Okay. Right. This phthalimide on reaction with 2-iodopropane in presence of, this is happening, that's why this is here. Okay. This phthalimide in presence of base with 2-iodopropane followed by aqueous acidic hydrolysis, we are getting, you see this one, 2-aminopropane, primary amine. So in this way, by changing alkyl group, we get a required amine. This is phthalimide, Gabriel phthalimide synthesis. Okay, we'll go to another preparation method, that is Hofmann bromide synthesis. Hofmann bromide synthesis. You see, what is Hofmann bromide synthesis? What are the different examples? What are the specific features of this method? Mechanism we'll discuss in detail. So what is Hofmann bromide synthesis? Hofmann is a scientist name who developed this reaction. Bromamide is a intermediate which is formed in this reaction. When we observe the mechanism, it will known. We'll see the what is bromamide. So this is also known as degradation reaction. Hofmann bromamide degradation. So degradation means in this method we will get 1 carbon less amine when compared to the starting amide. This is a Hofmann bromide reaction. So what is Hofmann reaction? First amide, you take amide. When it reacts with 1 mole of bromine in presence of base like NaOH or KOH, you are getting amine or NH2 along with the sodium carbonate and sodium bromide and H2O. These are the byproducts. So anyhow, we are getting this. You see, observe carefully, this amine is changing into amine. That's it. So what is happening here? One CO group is losing as CO2. This CO2 is adding to NaOH, we are getting Na2CO3. Okay, so this is the reaction. Amides, when these react with bromine, especially 1 mole of bromine is required. If you use 1 mole of bromine, what happens? Don't we get the bramines? A different reaction takes place. It is known in the mechanism of the reaction. When amides reacts with 1 mole of bromine in presence of NaOH, okay, we'll get amines. In this method also we can prepare primary amines. So in this method we can prepare aliphatic as well as aromatic amines. In the previous method, with the Gabriel phthalimide method, we can't synthesize aromatic amines. Why? Because let me explain. I forgot to explain. So whenever the alkyl halide which we are using, it is going nucleophilic substitution reaction. When in the case of alkyl halide, it is possible. Whereas in the case of aromatic halide X minus is in conjugation with the aromatic ring. That's why halogen's carbon bond is double bond in nature. So generally double bond and carbon halogen is not dissociated into X minus, not as easy as in aliphatic carbons. It's very difficult. That's why from Gabriel synthesis we can prepare only aliphatic amine. No, we cannot prepare aromatic amines. But in the case of Hoffman bromide reaction, we can prepare aliphatic as well as aromatic amines. Okay, this is a Hoffman bromide. What are the examples? You see different examples. So first take acetamide. You see CH3CO NH2 is the acetic acid amide. Amides are acid derivatives of carboxylic acids. Amide with 1 mole of bromine with KOH, it is giving methylamine. Okay, so acetamide is converted into methylamine. So in second example, benzoic acid. Benzoic acid, benzamide. Benzamide is converting into aniline, amino benzene. You see, one CO group is losing as CO2. That's why benzamide is giving aniline. So this is different examples for Hoffman bromide reaction. Once again, what is Hoffman bromide reaction? So in this reaction, amides, okay, amides on react with the bromine in presence of base, it is giving amines. It is developed by Hoffman scientists. That's why it is called Hoffman bromide reaction. Let us look about mechanism. Okay, what are the different general features? So we can already I told you we can prepare a primary amine. We can't prepare secondary or tertiary amines with this method. We can prepare aliphatic as well as aromatic amines with this method. We can prepare, in this method we are getting isocyanate as a reaction intermediate in this course of reaction. It is a unimolecular reaction. Okay, then if asymmetric group R group is in asymmetric carbon, we can get we will get the product with the retention of configuration. If optically active compound is taken as an amide is optically active compound, where in the case R is a asymmetric group, we'll get the same asymmetric same configurated amine, primary amine. That is in this case that is proved that there is a rearrangement reaction taking place with retention of configuration. In this reaction, only 1 mole of bromine is used. If you use more than 1 mole for 1 mole of substituent, 1 mole of reactant, the reaction doesn't proceed. That means another reaction of another course of reaction is proceeded. That's why you don't get our required primary amines. These are the different specific features of this reaction. Okay, then next slide, which is a mechanism. See mechanism carefully. See carefully. First, amide is our starting compound. Amide on reacts with base which abstracts proton from NH group. NH2 is a link to carbonyl group. It's an electron withdrawing group. Due to electron withdrawing nature of this carbonyl group, that hydrogen attached to nitrogen becomes a polar bond. Okay, that's why it becomes acidic. There are 2 acidic hydrogens. That's why one of the hydrogen is lost as H plus to the base hydroxide ion. After this losing of proton, we get this minus anion. It is stabilized due to resonance with this minus ion is minus charge is in conjugation with the carbonyl group. That's why it is stable. This stable anion, when it reacts with bromine, Br, so it substitutes one of the Br minus Br. So the one Br is leaving as Br minus, our nucleophile is occupying its place. That's why it is called nucleophilic substitution reaction. After nucleophilic substitution reaction, what will get? You will get a N-bromoamide. You see, this is the N-bromoamide. That's why this reaction is known as bromamide reaction. I already told you. In this course of the reaction, we will get one intermediate named as with name N-bromoamide. You see, one of the hydrogen is occupied by bromine. That's why it is called N-bromo. This one is N-bromoamide. This N-bromoamide, what is going is, there is a 1 molar of one acidic hydrogen on nitrogen. It is more acidic. Why? Because in previous the case, hydrogen is linked to only carbonyl group. In addition to carbonyl group, this hydrogen is linked to carbonyl group as well as bromine. These two are electron withdrawing. Due to the electron withdrawing nature, this hydrogen becomes more acidic. Further, if we don't use excess bromine, only 1 mole of bromine is required. Why? I'll tell you. So after losing this proton, this hydrogen as place will get 1 more ion. So N-bromonitrine. If we use bromine excess, one more bromination reaction this type of reaction takes place once again. After by getting NN-dibromoamide, what we don't want. If we get 1N-dibromonitrile, we don't get primary. I mean, that's why the reaction, this type of reaction doesn't take place. That's why we require only 1 mole of bromine per 1 mole of amide. So after formation of this this type of N-bromoamide, nitrine, this Br goes as Br minus. This electron pair delocalizes to this bond. At the same time, this R group is shifting from carbonyl carbon to nitrogen. 1,2 shift of R group takes place. So this is one type of specific rearrangement reaction taking place within the group. Internal rearrangement taking place. After this internal rearrangement, we'll get this isocyanate. This isocyanate on hydrolysis with water, reaction with water is giving NHCOH. After removing of CO2, we will get this primary. I mean, this is a mechanism of this Hofmann-Bromide reaction. I will repeat once again. Amides, on treating with the base, it loses one of the hydrogen as a proton by forming this type of anion. This is stabilized by resonance. This resonance stabilized anion on reaction with bromine, it undergo nucleophilic substitution reaction. It replaces one of the Br as a Br minus by getting this type of N-bromoamide. That's why it is a reaction intermediate. That's why this reaction known as bromide reaction. This bromide loses one more proton to the OH minus by getting this N-bromonitrine. This N-bromonitrate on rearrangement. This is a major step. This is a very important step to be understood. So N electron pair gives to the carbon bond, carbonyl carbon. The driving force of this step is electron pair is attracted towards a carbonyl group. This Br is going as Br minus, leaving as Br minus. At the same time, our alkyl group is shifting from carbonyl carbon to next carbon nitrogen as with its electron pair, that means R minus. So R group is shifting along with bond electrons to the nitrogen. That's why it's a specific rearrangement reaction. After this rearrangement reaction, we get this isocyanate. This isocyanate, it is usual reaction on acidification or on hydrolysis, on reaction with water, we get finally amine. By losing one CO2 molecule, we will get amine. So this is a reaction. So anyhow, we are getting amines from amines. So we are getting amines from amides. That's why it is a degradation reaction. So one carbon is losing as CO2. This is the mechanism of our Hofmann bromamide reaction. Next slide. There are some examples, some more examples. You see, this is an amide with some symmetric group. So this is amide. This amide is converting as amine. So configuration of R is same in the reactant as well as product. So as we already discussed, I told you that in this course of reaction, if there is an asymmetric carbon is there, so retention of carbon takes place. That's it. Next, second example, you see, okay, this is also amide. Reaction conditions of bromine and NaOH. Okay, so this amide is converting into amine. That's all. A carbon nitrogen bond is formed, new carbon nitrogen bond. So this is a new CN bond. In this method, we observe a new CN bond is formed. Okay. Then one more example. You see this one. This is amide, amine. That's all. So don't get confused by seeing a complex structure of amides. Just you see it's amide or not. If it is amide, whether an NaOH or KOH base and halogen is there or not. And that's why that reaction takes place. So you see a very interesting reaction here. It is a urea NH2 CO NH2 on Hofmann bromide reaction. That means a reaction with the base and bromine. CC simply losing one CO2 molecule after losing CO molecule, you are getting hydrazine. It's a very interesting NH2. A compound with NH2 amine diamine is called hydrazine. So in this way, hydrazine is prepared from urea. It's a very interesting reaction. Okay, so this is a Hofmann bromamide reaction. Okay, so in Hofmann bromide reaction, what happens? Amides are converting into primary amines. It is a degradation reaction. We are losing one carbon less. We are losing one carbon as CO2. It's a it's a reduction reaction. Why? Because we are losing oxygen. We can say reduction reaction. We can prepare aromatic as well as aliphatic amines in this reaction. If you take benzamide in this reaction, we get aniline. So aliphatic as well as aromatic amines we can prepare. In this reaction, we are getting N-bromoamide as a isocyanate and bromosnitrine are the intermediates. So stable is isocyanate. Okay, this is a Hofmann bromide reaction or degradation reaction. So let us discuss one more reaction which is in our syllabus, Schmidt reaction or Smith reaction. This is also a rearrangement reaction. Okay, what is happening in this reaction? We can see in Smith reaction what happens. Acids, when these acids, that means especially carboxylic acids, when these acids react with hydrozoic acid, this is very specific, hydrozoic N3H, N3H. So NH3 is ammonia, N3H is called hydrozoic acid. It has some specific structure. We will see the structure later. N3H is hydrozoic acid. When acids react with hydrozoic acid in presence of concentrated sulfuric acid, we are getting primary amines. After a rearrangement reaction, what is happening? Acids are converting into amines. First case, thaliamides. In the second case, amides. In this case, acids are converting into amines with one carbon less. You can also say it's a degradation, one carbon less. Not degradation exactly, it's changing its functional group. Okay. So this is a Smith reaction. In Smith reaction, carboxylic acid, when it reacts with hydrozoic acid in presence of concentrated sulfuric acid, we are getting primary amines. In this method also, we can prepare only primary amines, no secondary, no tertiary amines are prepared with this method. This is Smith reaction. If you see, observe carefully, we have three acids, one carboxylic acid, one hydrozoic acid, and sulfuric acid. This is a very interesting thing. All three acids are reacting to give primary amines. Okay, so what are the different specifications? So in this method, carboxylic acids are converted into amines, carboxylic acid to amines. In this method, we are using hydrozoic acid, sulfuric acid, and are used. Okay, then nitrene isocyanate or intermediates formed. Aromatic amines also we can prepare with this method, as in Hoffman method. How do we get the hydrozoic acid? This is a very thing. Okay, when sodium azide reacts with the acid, you'll get hydrozoic acid, HN3. So this is something about Smith reaction. Okay, next we'll go to mechanism. So this is the structure of hydrozoic acid. You see, observe carefully. This is hydrozoic acid is in two resonating structures, stable. So after electron delocalization of electron pair on nitrogen, we are getting two structures, what we call as resonance structures. So when one molecule in more resonance structures, we can say that is stable. Now this is also stable. Then, so what is the mechanism? First, this acid, our carboxylic acid is a starting compound. This acid on acidification, that means on protonation. Why protonation occurs? So carboxyl group is electron, maybe okay, electron deficient is not different thing. First, acid, concentrated sulfuric acid gives proton, required proton. This proton adds to the carbonyl oxygen. Why? Because this oxygen is having two electron pairs. By donating one electron pair to the proton, this oxygen gets protonated with O plus charge. Oxygen doesn't bear plus charge, that's why soon after its formation, it attracts its pi bond electrons from carbon to oxygen by forming this specific carbocation. It is a one intermediate. This is a carbocation with two hydroxy groups. This carbocation formed in the first step, it reacts with it adds with the hydrozoic acid. One of the hydrogen containing nitrogen, it donates electron pair to the carbonyl carbocation by forming CN bond, this one. So carbon with two hydroxy groups, it easily loses water by getting this type of acid azide hydrogen, okay, compound. By losing one proton, it will get okay, by losing, okay, by losing, you see, by losing one proton, we'll get a nitrogen will getting one type of this compound. After losing nitrogen molecule, they are getting this type of compound. Finally, it loses proton 2 by forming a nitrene or CON. It is a specific reaction intermediate, what we call is nitrene. Nitrene also one type of reaction intermediate like carbocation, carbanion, carbene. So this is a new one more reactive intermediate we come across in organic reactions. So this nitrogen undergo a rearrangement reaction, this electron pair moving towards carbonyl carbon. At the same time, this R group is shifting from carbon to nitrogen along with its electron pair. So due to this specific rearrangement reaction, we are getting isocyanate. We know isocyanate is very reactive with water. It forms hydroxamic acid. Then on decarboxylation, you are getting amine. So from acid we are getting amine. This is a mechanism of this reaction. Once again, I repeat, first in the mechanism, first carboxylic acid undergo protonation. This proton adds to oxygen. This oxygenated carboxyl group forms carbocation. So O oxygen plus charge is unstable. It attracts bonded pair, pi bonded pair from carbon by forming carbocation. This carbocation attached to hydroxylic acid following by dehydration and losing nitrogen molecule, and lastly proton, we are getting nitrene. This nitrene on a rearrangement reaction we are getting isocyanate. This isocyanate on reacts with water and elimination of eliminating CO2 molecule, finally we are getting amines as a product. This is a primary amine. In this way we can get primary amines in this method. It is a mechanism for, this is a mechanism or synthetic route or different steps involved in the conversion of acid to primary amines. We'll get two more examples. You see, you have taken butanoic acid. This butanoic acid on reaction with the hydroxylic acid and in presence of concentrated sulfuric acid, we are getting propylamine, 1-aminopropane, that means propanamine or propylamine. So this is a Smith reaction. You see, hydrochloric acid is also there. Whenever the reaction condition, we will observe a hydrochloric acid and concentrated sulfuric acid, the carboxylic acid easily converts into corresponding amine. We have to notice that it is a Smith reaction. So finally, one more example. It says, you see, this is a trimethyl phenyl carboxylic acid. It's a benzoic acid with two ortho positions and para positions occupied by methyl groups. So this is a trimethyl benzoic acid and react with hydroxylic acid and sulfuric acid. In presence of sulfuric acid, we are getting trimethyl, that means trimethyl phenyl amine. So aniline derivative. So in this way we can get aromatic as well as we can prepare aliphatic as well as aromatic amines. So this is a Smith reaction. Okay. So today we discussed, what we discussed today is, once again I quick recap. In this session we have discussed three organic name synthetic reactions to prepare amines, especially primary amines. In the first we discussed what? Gabriel phthalimide synthesis. What is this? Phthalimide in presence of base, when it reacts with alkyl halide, it will give alkyl amine. In this method we can prepare only aliphatic amine. Why? Because in the course of the reaction a nucleophilic substitution takes place with alkyl halide. In aromatic halides, halogen bond is not goes as X minus due to double bond nature with the aromatic ring. So this is a Gabriel phthalimide synthesis. In second, we discussed Hoffman bromamide synthesis. In this Hoffman bromide synthesis, M1 mole bromine is used. Amides are converting into amines. Amides, when reacts with the bromine, 1 mole of bromine in place of base, it converts into corresponding amines. That's why it is Hoffman reaction. In the course of the reaction, we will see one of the reaction intermediate is N-bromoamide. That's why it's called bromamide reaction. It is a degradation reaction. Why? Because amides are converting into amines with one carbon less. It is a degradation reaction. We've seen mechanism 2. Okay. By this method, we can prepare aliphatic as well as aromatic amines, primary amines. Next, we discussed the Smith reaction, Schmidt reaction. In the Smith reaction, acids, carboxylic acid, when these react with hydrozoic acid in presence of concentrated sulfuric acid, we are getting primary amines with one carbon less. With this method also we can prepare aliphatic as well as aromatic amines, primary amines. We discussed about mechanism and discussed this reaction with some more examples. This is today's class. In the next class, we'll discuss physical and chemical properties of amines. Thank you very much. Thank you.